So you see, essentially the tools that we're going through now were known to Born and Fock, but then still, like 60 years later, a new idea or something like Barry discovered something remarkable from it, and then that has sort of opened up a whole new range of stuff that we can do. So I'll not talk too much about the Barry phase because Massimo's somewhere around here and he's really the expert. But I'm told we can get going. So, okay, so what I'm going to start with is adiabatic theorem. So we're going to go back to our quantum mechanics 101, and really the essence of what I want to discuss is thinking about, well, how does a quantum system evolve? So I will just add one more technical note. Don't worry too much about, take notes if you feel more comfortable, but I have a PDF of what I'm going to be going through here. That's going to be sent out to you guys afterwards, so you don't need to try and decipher my chicken scrawl up here while I'm sort of talking and writing. Okay, so my question is, how does a quantum system evolve under a time-dependent drive? Okay? And that simple question, what we essentially need to answer it is two ingredients. Okay, so everything I'm going to discuss today is for closed unitary dynamics. Nice, simple stuff. So one, our classic time-dependent Schrödinger equation, which we all know, dt psi of t is equal to h of t psi of t, and my time-independent Schrödinger equation. Okay. So h, and so we'll use n as our eigenstates. We have eigenenergies and eigenstates again. Okay, so this, I'll call this equation 1, this equation 2. We'll come back to these a couple of times now. So, for a time-dependent drive, I've got my system, closed evolution. I'm varying the Hamiltonian in some way. And I want to know how is that system evolving without putting any particular restrictions on how I'm varying the Hamiltonian. I'm just doing some time-dependent drive on it. Well, I can start with my time-independent Schrödinger equation. At every instant in time, the system has to satisfy the time-independent Schrödinger equation. So I can think about an instantaneous solution. Okay? So for my time-dependent drive, I'm varying my Hamiltonian in some time-dependent way. This guy, I can write down some time-dependent, but these are like instantaneous eigenstates. So this is just my time-independent Schrödinger equation written, say, it's sort of at instantaneous time. Okay? So my n of t, that's my instantaneous eigenstates. My En of t, that's my instantaneous eigenenergies. Now we know from our quantum mechanics 101, that forms a valid basis. So I can then use that information to say, okay, let me think about those instantaneous eigenstates as the basis that I want to write my, my general solution to the time-dependent Schrödinger equation in. Okay? So we use the set, these eigenstates, as a basis for the solution of the time-dependent Schrödinger equation. So I just write down some ansatz solution to the time-dependent Schrödinger equation. So this is going to be the sum over n of some coefficients, which are time-dependent, times these instantaneous eigenstates. Okay. So far, nothing beyond basic introductory quantum mechanics. I take this expression now, and I plug this guy just into my Schrödinger equation. So if I plug in to the time-dependent Schrödinger equation, so into 1, what I have is I h bar time derivative, and then I just plug in what my psi of t is, so using this ansatz solution, sum over n of Cn of t, n of t, that is equal to my time-dependent Hamiltonian h of t applied to this ansatz solution, Cn of t, n of t. Okay. Now, everything that I'm doing, so you'll see that every term here is essentially time-dependent, so I'm going to make the notation a little bit more brief. So we're going to just drop the explicit time dependence from now on. Just remember, every time I write down a C of Cn or an N or a H, all of them are implicitly time dependent. Okay, and then we're going to use the dot notation just to denote time differentiations. Okay, so with those we can just work out, we can just expand out what this is. So then we have I h bar. If we take the time derivative of that ansatz wave function, what I'll be left with is, so I still have the sum over n of time derivative of my coefficients plus Cn times the time derivative of my eigenstates. And then I can use spectral decomposition of my Hamiltonian, so I can always write that in its energy, in its instantaneous energy eigenbasis as well. So now I'll have a double sum on this side. So let's just have a dummy index k and n. So I can take the decomposition of the Hamiltonian. That's E k with these eigenstates. And then I have my instantaneous eigenstate n, and I still have my coefficient Cn. Now I can just tidy this up a little bit. I get I h bar, and I still have sum over n of Cn dot n plus Cn n dot then equal to, and then what I have here, obviously, these are, I've just taken the spectral decomposition, the at every instant in time, and n of the n's are all my instantaneous eigenstates, so this is just a Kronecker delta. These are the eigenstates, so this is just delta kn. So I can simplify one of those sums, will disappear, and so I'll just simply be left with, again, the sum over n of Cn, my coefficient, En, my energy eigenstate, or eigenvalue, n. Okay. Again, still not doing anything too unfamiliar to us all. And really what we're interested in doing in order to solve the Schrödinger equation, really what this boils down to is, just finding the dynamical evolution for these coefficients, these Cn's. Okay? So that's what we want. So how do we get the differential equations for the Cn? We want to project onto some eigenstate, the nth eigenstate of h of t. So you remember that. So now I take my nth eigenstate, I just slap it in on the left-hand side and bring it through. What I have is I h bar, and have sum over n of, I still have Cn dot, and then here I will have an mn plus a Cn m n dot. That should be equal to, and then on the right hand side we have a sum over n of Cn E n m n, these inner products. Okay. Now, again, we have the fact that all of my m's and n's, these are all just the instantaneous eigenstates of the original Hamiltonian. So when I have these inner products, these guys are just Kronecker deltas. This is delta mn. This guy is a delta mn. But the guy that's a little bit more complicated, this guy, What is m n dot? And really, this is the guy where the adiabatic theorem emerges from, and where all of the interesting physics about finite time processes comes from. And that's the guy that we're going to be interested in trying to pick apart and understand a little bit deeper. But let's just keep on plugging on with this straightforward derivation of the adiabatic theorem. So, the fact that these guys are Kronecker deltas then means I can simplify a lot of these sums. In fact, the only term where the sum is meaningful is in that point where I have the m n dot. That's the only one where I can't get rid of all of the sums. So that's the only place where I need to keep the sum in. Everywhere else I can basically strip it away down to just a single term. So we can simplify. I h bar, and so I have so Kronecker delta, whenever m is equal to n, I get the term survives. Whenever m is not equal to n, it disappears. So I will have a c m dot plus, now I'm going to do something here where I'm going to split the sum. Let me see, where am I? Can we see, just about see that, can we? Yeah, the red dot, yeah. So in here, so I'm just looking at this more awkward term. I have a sum over n of this term. And what I've said is this is the only one where the sum plays any role. Now, what we're going to see is this term only survives when m is equal to n. Same with this term, only survives when n is equal to m. So I'm going to extract out the term here whenever I have m equal to n. So the coefficient that will be cm m m dot. That's going to be a term on its own. And then I'm going to leave the sum where it'll be the sum over everything where m is not equal to n. And that's where all the interesting physics comes in. So let me just write that down explicitly here. So I have my term cm dot from the first. I extract the m equals n value of the sum for the second term. So I'll have a c m m m dot. And then what I have left over from the sum over m not equal to n of cn m n dot. So that's everything I have on the left-hand side. And this guy is equal to c m e m. Okay. So, take a second for now. What we've done, we've just asked the simple question, what happens whenever I have a time-dependent drive, unitary dynamics? I took my time-independent Schrodinger equation and said, that guy gives me a valid basis to write the solution of the time-dependent Schrodinger equation in. So at every instant in time, I can always express the time-evolving state in terms of those instantaneous eigenstates. I use that fact, slapped it into the time-dependent Schrodinger equation, and then I've just sort of worked through the derivatives here. And what we're left with is this expression. So now we want to see, well, can we write down a way to solve this? Can we find a solution to this guy that allows me to express, well, what is the time evolution of the system? So, if I start bundling things together, that makes sense. I have I h bar cm dot. So that's the time derivative of my coefficient I'm interested in. And then I'll take everything across the equal sign. Is equal to, so what I have will be a cm em minus an I h bar cm m m dot, and then minus I h bar, and then the sum over m not equal to n of cn m n dot. And if I just factorize out that cm, so I have an I h bar cm dot is equal to, well, here em minus I h bar m m dot Cm minus this I h bar, this awkward term, this term with the sum, not equal to n Cn m n dot. And this is our important guy. This is what I'm going to call equation 3. Because, now, let's have a look at what we have here. This is pretty much what we always have. If you, again, you go back to any introductory quantum mechanics textbook, this is what you end up with whenever you want to solve the Schrödinger equation, if everything is nice and simple. In fact, I have a straightforward differential equation. So if I only had these terms, then I can write my normal stuff, my normal differential equation for the coefficients is then equal to minus I over h bar Em minus I h bar m dot, which then you can simply integrate and you'll get what your coefficients are. Cm, your time-dependent coefficients are then given by e to the minus I over h bar integral between 0 and t of this guy, Em minus h bar m dot. Yeah? So, standard stuff that we get from our usual quantum mechanics 101. But that is only if this term here is vanishingly small or is essentially negligible. If I can neglect that term, then I can solve the dynamics exactly, and everything's nice and easy. All of my interesting stuff to do with non-adiabatic dynamics comes from that second term. And that's what we're going to see gives rise to protocols for quantum control. And in fact, feeds into huge, like really lots of interesting areas. So we'll talk a little bit about things like Kibble-Zurek mechanism and stuff like that when we get into it. But I think, I have plenty of time. Just as an interesting aside here, if we just for a second, just have a little look at this simple solution. So if I were able to neglect that last term, that term that involves the m n dot inner product, and I can just solve my simple Schrödinger equation, what I'm left with here, and in fact, if you look at the derivation by Born and Fock, so they erroneously assumed that this slightly weird term, m dot, was equal to 0 for all times. But that's not actually the case. So I can take my solution whenever I'm able to neglect this term with the sum, whenever I can just simply solve my Schrödinger equation, I can write that exponent. So I can write e to the minus I over h bar is integral 0 and t of Em minus I h bar m dot. I can write this guy as the product of two phases, e to the I theta m of t, e to the I gamma m of t, where this theta m is equal to 1 over h bar sum from 0 to t of Em of t dt, and my gamma m is equal to I, this integral of m dot. So you'll recognize this theta m, that's just what you get from your normal, just standard solving the Schrödinger equation. This is what we call your normal dynamical phase. So it just comes from the fact that if you have an eigenstate, it'll pick up a global phase that's just related to whatever its energy eigenstate is. So that's just your normal thing that we always see. This term This is the thing that Fock and Born neglected. They said it's always 0 for all values of t, so they just completely ignored it. This is what Berry realized in 1987 wasn't always the case. There are instances where that term is non-zero. And so, weirdly, while we normally associate like that global phase that comes from the sort of dynamical phase as really not being something that's measurable, this phase is what we call the geometric phase, or more often it's called the Berry phase now, and this guy is actually measurable. And in fact, if you catch Massimo at some point before he leaves, he'll be able to tell you an awful lot more about it than I can. I mean, people have been using this, have realized that geometric phases, because they are measurable, you can exploit this very weird effect that comes really just from the basic derivation of this adiabatic theorem to get states where you can do things like certain quantum computations and everything using the fact that you get this measurable phase that appears. Something that was largely neglected, took us 60 or 70 years to realize, no, actually there's something there for us to look at. So, okay, that's just a little aside. So if you ever hear or see stuff referring to geometric or Berry phases, that's the guy that we're talking about. But okay, let's go back to thinking about this equation. Okay? So now it should be obvious. If I can neglect that last term, then I can solve the Schrodinger equation. And imagine I started in an eigenstate. So imagine that at my initial time, I only had one non-zero coefficient. So my Cm was equal to 1, and all the rest of them were 0. Then whenever if that last term is negligible, if I can neglect that term with the sum, then you see I have the differential equations will all be uncoupled. So if I only start with only one eigenstate, if I start with my system in just one of the energy eigenstates, and then I do a time-dependent drive in such a way that that last term, that awkward sum, is negligible, is not there, then the system will always stay in that eigenstate. This is the sort of intuition of the adiabatic theorem. If I start in an eigenstate and I am evolving the system sufficiently slowly, that's the problem with the sort of heuristic argument is what do we mean by sufficiently slowly? But if we can neglect that last term, then if I start in an eigenstate, I remain in an eigenstate. The only thing that happens is I'll pick up these dynamical and geometric phases. But otherwise, if the system starts in an eigenstate and I can neglect that last term, it stays in an eigenstate. So let me just write that down. So if it starts in an eigenstate, then let's say that my Cm at time 0 is equal to 1, and all other coefficients are equal to 0, and the last term in 3 is negligible, the system evolves staying in the state M, only getting the above phases. That's just what I was just saying. So if I start in an eigenstate, then the only thing that will happen, if I can neglect that last term, is that it'll just start picking up these dynamical and geometric phases. That's the only thing that happens. Okay. So now, how to understand that last term? And how does it relate to understanding how we achieve quantum control? Like what's the role it plays in us determining methods or protocols in order to manipulate quantum systems? So that last term is minus IH bar sum over M not equal to N C N M N dot. If we want that guy to be small, well, let's have a look at it. Like what way can we make this guy negligible? can't do anything about I and H bar, can't do anything about the CNs. Remember, even if my CM, if I start in a specific eigenstate, this sum is to do with all of the couplings. It's how the mth eigenstate that I've started in gets coupled, how all of my other coefficients that were initially 0, all of my other n's, all of my CN's at the initial time are 0, but because of this term, they could become non-zero. Okay? So I can't assume or can't say very much about what these CN's are. That's really what I want to solve for. So the only way that this term can actually be set to be negligible, to really say that I can get rid of it, we would require that m n dot goes to 0. And this is what we want to understand. This is really the essence of the adiabatic theorem, is to say in a more, rather than a sort of hand-wavy way, to say in a much more precise way, in what instances can we neglect that term? And it all comes down to understanding what this m n dot is. So let's look at m n dot a little bit more carefully from 2, the time-independent Schrödinger equation. So I have my time-independent Schrödinger equation, which is what I use to build my ansatz solution for everything in the first place. So I have my h n is equal to E n n. And again, remember, this is all, there's implicit time dependence everywhere here. Okay? This is the time-independent Schrödinger equation for the instantaneous solution. So at every instant in time, the system obeys this equation. I can differentiate this guy. So I'll end up with h dot n plus h n dot is equal to E n dot plus E n n dot. And now, well, what do I want to check? I want to get this product, this scalar product, m n dot. So I do exactly what I did before. I'm going to project onto my mth eigenstate now and see what I get. So again, project onto m. And again, I just want to stress and recall, in this term, remember, a few steps before, I explicitly excluded the case whenever m was equal to n. That was a special case that then entered into what I ended up defining as the Berry phase. Okay? So this sum is only concerned with instances where m and n are different. So m is not equal to n. And so then what I'm left with, I have m h dot n plus m h n dot is equal to E n dot m n plus E n m n dot. So again, done nothing particularly, nothing beyond our basic quantum mechanics again. So again, I have another Kronecker delta guy here. By construction, this guy has to be equal to 0 because again, remember, m is not equal to n. This is Kronecker delta, so that term definitely disappears. And then here, I have m applied to h, so that guy is just going to give me an E m m n dot. And so if I simplify this down a little bit, I have m h dot n plus E m m n dot is equal to En M N dot. And now I just rearrange things around a little bit because what I'm interested in is understanding this M N dot guy. So if I bring things across and rearrange it, what I'm left with is that M N dot is equal to M H dot N divided by E N minus E M. If that guy is roughly 0, implies I get adiabatic dynamics. This is your adiabatic theorem. Okay? What it's saying is that the condition required for if I started in an eigenstate and I was to do this arbitrary time-dependent drive, closed system unitary drive, then in general I would get some excitations. I would get some coupling between the eigenstates. But I can very precisely write down what that term is, and I know that it's dependent on this scalar product M n dot. So the question is, if I want adiabatic dynamics, then that term has to go away. And in order for that term to go away, the only way that that can happen is if this expression is small, if this guy is 0. So what I essentially need is, and now you can kind of see that whenever we talk about adiabatic dynamics, there's actually two things. If that term wants to disappear, I either need this guy to be really big or this guy to be really small. Normally when we talk about the adiabatic theorem, we talk about the numerator here being very small. Whenever you first encounter the adiabatic theorem, very often we talk about it as this notion of sufficiently slow. If I drive a system sufficiently slow, what sufficiently slow means is that such that the rate of change of the Hamiltonian essentially vanishes. You know, it's so slow, and okay, there's this additional term to do with the energy difference between the energy levels that are being coupled. If that's reasonably big, or of some order, and the drive is sufficiently slow, that term will basically vanish. And if that happens, then I recover adiabatic dynamics. So my system, if I started in an eigenstate, it would evolve collecting those adiabatic phases, the geometric phase and the dynamical phase, but it wouldn't leave that eigenstate. It wouldn't leave if I started in a ground state, it won't leave the ground state manifold. This term is it captures really the essence of what's happening to the system due to the fact that I'm doing a finite time drive. And it turns out this is incredibly important in a whole range of areas. Like, we're going to look at it now in the context of control. But in fact, I guess if I have time, yeah, I should do. I'll probably run for about another 45 minutes to an hour. Probably towards the end, I'll talk a little bit about some stuff I've done with the quantum control in the context of many body systems. And what you'll find is that there's a thing called the Kibble-Zurek mechanism, which is to do with how a many-body system reacts to a time-dependent drive, is essentially just a more careful interpretation of the adiabatic theorem. That's really all the Kibble-Zurek mechanism boils down to. It splits the system's response up into what it's called an adiabatic and impulse regimes, and really it's defined in terms of basically what this adiabatic basically comes from the adiabatic theorem anyway. So we'll see that a little later on. Okay, happy enough for this? Again, like I say, if anyone went through Griffiths, that will have all been very, very familiar to you, but hopefully got everyone onto the same page. In fact, if you look in Bourne and Fock's paper, essentially the derivation we did there, that's pretty much what's in there. So we've done nothing new from the late 1920s. And Cato's extension of it, or it was a slightly more careful formulation, but basically is much the same. A few subtleties there that maybe I glossed over or that I didn't make explicit. I made implicit assumptions there that the spectrum was non-degenerate. You can adapt this derivation to situations when you have degeneracies in the spectrum. It doesn't change the derivation very much. It just makes it a little bit more cumbersome. But the essence of what we went through basically follows over. So main point is that this was all known back in the late 1920s, but how does this apply to control? Well, if we think about this term, captures very precisely. Yeah?
Is there any, you can have geometric phase even if the dynamics is at the top.
Yes.
So there is an intuition where you can neglect this, but you cannot neglect Graham, cat, and dot.
So we assume, like whenever you have adiabatic dynamics, you are assuming you can neglect this term. So you are imagining you're in a physical situation where this term itself is vanishing. You know? So that means there's no coupling across the eigenstates. So then if that term's disappeared, what you're left with, you still had this term m dot, which is where the Berry phase comes from. Intuitively, if you were neglecting all of those sums, you would not, and this is essentially what Born and Fock said. They were like, oh, okay, all of them are zero, even the one when m is equal to n. So the m dot is also equal to 0. And in a lot of instances it is. But whenever you have like a closed path, and it turns out that you collect this geometric phase, it's very not obvious. Believe me, I mean, like, you have to go to Berry's paper, and you'll see there where he more carefully, at least I think, yeah, he would do, where he more carefully goes through it, and you see that there are instances where you can't neglect this term. Even if the rest of the sum, you're in a situation where there's no coupling across the eigenstates, that's the kind of the subtlety. If you're not coupling across the eigenstates, that non-adiabatic term, the theorem we just derived, that guy disappears. But if you're in the eigenstate, well, that eigenstate is changing in time. So you have something to do with the m dot. But whether or not you can set it to 0 or not becomes, it becomes much more subtle. So I'm definitely not answering your question in any particularly meaningful way, except to say, there's a reason it took 70 years for us to discover it, I think. So if you go and have a look in Berry's papers, or I think best thing is just find Massimo and accost him and tell him to explain like the Berry phase to you, you'll see it. Yeah? Okay, but so this term that I'm interested in the context of control, this guy captures very precisely, I guess what we could call the adiabatic error. Due to the finite ramp. So adiabatic error in the sense that if it's vanishing, if I can neglect the term, then my dynamics is adiabatic. If I can't neglect it, then I have some excitations. I have some coupling across the rest of the spectrum. So I'm calling this my adiabatic error. That's like how far I'm deviating from perfect adiabaticity. So this very precisely captures it. And if you look at the expression, where did I write it down? Here. Well, how would I be able to recover adiabatic dynamics in an arbitrary case? All I would want is a situation when I can get rid of that term. What I've assumed here for adiabatic dynamics is that it's negligible. I'm picturing physical situations when that term is sufficiently small that it can be neglected. That happens whenever the rate at which I'm ramping the system is really slow, such that the numerator of that guy disappears, or when the energy difference is so large that it vanishes. In those two instances, this term disappears and I get adiabatic dynamics. But what was not maybe explicitly appreciated, or probably it may have been noticed, but back in the late 1920s, nobody thought that this was a meaningful observation. I could get rid of it just by, this is minus IH bar sum of blah, blah, blah. If I just add that term in, if I take a plus IH bar sum of blah, 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 they'll cancel, right? Welcome to quantum control. That's what Berry did. So in fact, if you look, what this term is telling you, mn dot, the coupling across the spectrum, this is given in terms of the matrix elements of the time derivative of the Hamiltonian rescaled in terms of what this energy difference is. So this is telling me the different matrix elements. I can build a Hermitian matrix, I can build a Hamiltonian that I can then just add to my system. So what I'd say is it was noticed, maybe? So this was in 2003 by Demer-Plack and Rice, and then independently in 2009 by Berry. So we'll see, like the actual, how they went about the derivations is not quite so, I'm being a little flippant here, saying they just noticed you could just add it on. It turns out that the route they took to finding these terms was a little bit different, but it boils down to that you can simply write down a counter-diabatic term. You can define, so we can define, so in the normal nomenclature we call this the counter-diabatic term, so this is the Hamiltonian that's going to counter-diabatic in the sense that it counters non-adiabatic transitions, okay? So, or it counters diabatic transitions. I H bar, and then I'm going to have double sum over n and m, and again remember n not equal to m of m h dot n divided by that energy difference, En minus Em. Such that if we evolve some initial eigenstate of my Hamiltonian, n, according to, and I'm going to reintroduce the time dependence explicitly here just to make it all crystal clear, h of t plus hcd of t this hcd term exactly counters, exactly suppresses the transitions due to the time-dependent ramp. And I think this is kind of, in some sense, not trivial, but it's sort of obvious now. After you've gone through the adiabatic theorem, you see the term that leads to the coupling. You see the non-adiabatic term, and all that counter-diabatic driving is doing is saying, okay, I know from the adiabatic theorem exactly what transitions I'm going to get. I am going to take I'm just going to add the term that exactly cancels that. And so if I evolve a system according to this h tilde, such that and I start I don't have to start in just an eigenstate here, but it's simplest for us if we think about it just as a ground state. Imagine I took my system, started in a ground state, I'm doing some time-dependent ramp. If I just ramp the system, I will get excitations, okay? That's what the adiabatic theorem is telling me. If I do it in a finite time, I will get some excitations. If I take this hcd term, and if I evolve according to h plus hcd, the transitions the system wants to make, this hcd term basically just bats them back down. So the system is evolving, wants to get a bit excited, the hcd term just sort of slaps it back down, and it just stays on its, if I started in the ground state, it'll just stay in the ground state. So this is counter-diabatic driving. Now, we'll have a quick, maybe for a quick couple of minutes, we'll have a little look at how Berry went about doing it, which it's essentially equivalent, but if you just want to go through it, just in case you do look at Berry's 2000. So I think Berry's paper is very nice. I think it's very pedagogical. He goes through basically the derivation. He flags up the adiabatic theorem, and then he talks about inverse engineering the dynamics. That's what we're going to talk about now. And he establishes that this expression is equivalent to the expression he derives. I just think that this term is much much more elegant, because it comes from the adiabatic theorem. Once you've done the adiabatic theorem, you have quantum control for free, essentially. It just turns out that if you do this Berry approach, this inverse engineering we'll look at, the terms are actually exactly the same. So, from Berry, 2009 JPhys. If we want a perfectly adiabatic dynamics, so a perfectly adiabatic dynamics then implies state will only collect the dynamic and geometric phases. So what I mean is that if I had a perfect adiabatic dynamics, so again, I'm just assuming I'm starting in an eigenstate of my Hamiltonian, and this is the guy I want to evolve. So I'm just keeping things simple by saying I'm evolving a single eigenstate of my Hamiltonian. So let's say I started in psi n. The time evolved state, let's call it big T, is going to be given by either minus I over h bar integral between 0 and t of my dynamical phase, en of t dt, minus then my Berry phase, n dot dt, n, and then the instantaneous eigenstate. If this is what I'm saying. If I wanted a perfect adiabatic dynamics, and I started in n, the nth eigenstate at time 0, then if it's perfect adiabatic dynamics, this is what my state should be at any later time. Okay, that's all I've done here is just written down the solution to the differential equation before, when we neglected that non-adiabatic term. So another typical approach in quantum control is this idea of what we call inverse engineering. We know what state we want to get, so what we say is, well, what dynamics will connect my two states? So Berry asked, how can we inverse engineer a Hamiltonian dynamics such that this state is exactly the solution of the time-dependent Schrödinger equation. I.e., what h tilde do we need such that my time-evolved state, so at time t applied to my initial state, which is in the nth eigenstate, is exactly given by this psi n of t. That's the question Berry asked. Okay? What Hamiltonian do I need that gives rise to a unitary that exactly takes my initial eigenstate and then puts it onto the time-evolved state, where all the time-evolved state, it has just collected those two adiabatic phases, and otherwise nothing else has changed. It's exactly in the instantaneous eigenstate at that time. So this is the question he asked. And then it gets a little bit more technical. I'll probably not wade too far into the details in this. So since any unitary, so any u of t, can be written as dt u of t h of t dagger of t. I can rearrange things here such that I can determine what my h tilde, my h bar, dt, u of t, u dagger of t. So this is just a mathematical relationship that is known. So I don't know how people derived it, but this is where we start from. We are able, if we have a unitary, we can then basically retrofit what work out what the corresponding Hamiltonian is that gives rise to that unitary using this expression. Since we want my initial eigenstate, my initial state, to go to this psi n of t, we choose what our unitary is. So we can choose what u of t is, and it looks a little bit more complicated than it is. Sum over n e. So all I'm writing down here is the state minus I over h bar integral t. So my dynamic phase, my geometric phase, and then I have the eigenstate, the nth eigenstate at t are producted with the initial state. Okay? So really all that I have written down here, I've just written down what my unitary is, and you can see this guy, that's psi n of t, initial state. So it just takes my initial state. If I start in the initial state, then it will just take me to the state I want. So I've just kind of, I know where I want to go, so I've just sort of by hand said, well, I know what I want to achieve. This is what the unitary has to be. I then want to work out what the corresponding Hamiltonian is. So, and this is where I use this relationship. So we've been going a bit. I'm not going to go through the derivation there. It's in the notes here. You can work it out. Take this u of t, plug it into that expression, and then do the derivatives, and you'll work it out. What you'll end up with u of t, so plug this guy into that expression, that guy up there. And we find that this h tilde is, we have a sum over n of en and n plus I h bar sum over n dot. This are the product minus n dot and n. Now, that does not look exactly the same as what we had derived earlier, but we'll see, well, we'll not really see too clearly. If you do explicit examples, it turns out to be exactly the same. In fact, I can split this guy up. The first term, that's just the Hamiltonian. That's just my original Hamiltonian. And then this second term actually turns out to be exactly the same. So this is exactly the same as that guy there. If you work them out, they're precisely the same things. So Berry's approach here, using this inverse engineering, gives rise to exactly the same thing that we got basically for free from going through just from the adiabatic theorem itself. Okay, we've been going like an hour at this point. Any burning questions or any issues, or have I lost everyone, or no, we're okay? Cool, okay. So phase transitions, that's a bit tricky. Okay, I'll come to that. At level crossings, this term, yeah, it gets a little bit difficult, because what this term does is that it suppresses transitions. So there is, it gets quite delicate. This term will basically fail, sort of fail, if you have a degeneracy, because it doesn't really know which eigenstate it's supposed to be in. There are extensions to this idea. So in Berry's derivation, what we've gone through again here, we've assumed no degeneracies. But again, there are ways where you make sort of minor adjustments to it to account for the degeneracies. I can't remember the precise effect that degeneracies have in the counter-diabatic term. I know in the adiabatic theorem it doesn't make too much of a difference, but it's a little bit more subtle in the counter-diabatic driving term. But there's been papers that have come afterwards. So. I can write down a term that is very, very similar to this counter-diabatic term, this HCD, that accounts for the fact that there's degeneracies. It's only, I think, only very slightly different. I personally haven't really worked on it at all. So whenever you get into phase transitions, in fact, that's where things get very interesting. Whenever you're dealing with trying to ramp a system through a critical point, then that's where, depending on the system you're dealing with, I mean, if you look at something like the Ising model, or essentially systems that have applied these control terms to, generally you'll find they're still gapped until you go to the thermodynamic limit. There are issues with these control terms before you get there, though. So once you start looking at many-body systems, this HCD term, I mean, I haven't said anything about the physical realization of what these control terms are. Very likely, this is probably part of the reason that back in the late 20s, whenever the adiabatic theorem was worked out, that nobody cared about the idea that you could cancel the transitions, because the Hamiltonians don't look particularly physical for a lot of systems. It's very nice for a single qubit that we're going to see now. So the next sort of 30, 40 minutes, we'll just sort of look at examples. But whenever you go to like even harmonic oscillators or to many-body systems, what this HCD term, the form it takes, is very complicated. It's basically, it is physical, but it's got highly non-local terms, like huge amounts of like products of operators. So it's not really experimentally feasible. But as a starting point, what I like about this is it gives a very straightforward recipe for achieving control that you can then build on. And that's what people have essentially done over the last 10, 15 years. Starting from this is to say, well, okay, I can achieve control. I have a meaningful Hamiltonian. How can I adapt it or modify it in such a way in order to do something a little bit more implementable or experimentally realizable? For certain systems, though, this is already sufficient. So that's what we're going to have a quick sconce at now. Is just the classic two-level system. So let's have a look at what happens for the Landau-Zener model. So as an example, consider the Landau-Zener model. So if you're not familiar, this is one of my favorite things to play about with. Nice, easy, two-level system. So if I have some sort of gap, then I have some time-dependent term applied to some field. Okay. Typical two-level system that I'm going to mess about with. I have the delta sets whatever the minimum energy gap is between the two eigenstates, and then what I'm interested in, the time dependence enters in through this ramp, this g of t applied to some, just imagine it as some applied maybe magnetic field. So what's very nice about this model, and why I love it so much, is it's very simple. It's a two-level system, so we can solve it pretty much. But it captures an awful lot of the essential physics of much more complicated systems. This is essentially where many people start before they start scaling up to proper, let's say, quote-unquote, proper many-body systems. So, and in fact, understanding everything about the Landau-Zener is already sufficient to gain most of the intuition you need for something like the Ising model. So when you go to and solve the Ising model, how you solve the Ising model is you transform it into momentum space, and then in that case it decouples into a whole bunch of Landau-Zener models. And if you understand the physics of the Landau-Zener, then you basically already know an awful lot of stuff to do with the Ising. So one of the reasons I love the guy. So we can write down the eigenstates. So my eigenstates are, let's say, my ground state, phi g, can be written as, let's say, cosine theta 0 plus sine theta 1. And then my excited state, so sine theta 0 minus cosine theta 1, where I'm assuming, let's say, 0 and 1 are eigenstates of sigma z, with tan of theta given by minus gt plus square root of delta squared plus g squared divided by delta. And my energies, the two energy eigenvalues, are plus and minus square root of delta plus g squared. So, we want to see what it takes to achieve control for the Landau-Zener model here. So I'm going to be ramping this field, and so we just want to take the Berry term and compute it and have a look at what drops out. So the counter-diabatic term. So if we use just the expression that we got from the adiabatic theorem, we get as I h bar, and then I have we had the outer product. So it's the sum over the outer product of the eigenstates whenever they're not equal to each other, and sandwiched between what the time derivative of the Hamiltonian was. If I look at my Hamiltonian, the only thing that's time dependent is this function g of t. So when I differentiate h, delta x disappears. I'm just going to be left with the time derivative of g times sigma z. Yeah? So I'm going to just get a g dot sigma z here. G dot sigma z. And then remember, the counter-diabatic term, if we scan back up here, where I wrote it down, whenever n is not equal to m. So because I'm dealing with a two-level system, I really only have the instances whenever I have the ground state, time derivative of the Hamiltonian excited state, and then the reverse of that. Okay? That's what the whole sum is going to be. So it's a very, very simple thing to work out. So I get here phi e divided by, and then I have the energy difference of Eg minus EE. And then plus, and then I have the other term where I just flip the indices essentially. I just swap the excited and the grounds. So I get phi e, g dot h, phi g, divided by EE minus EG. Okay, and now, now you just plug this into Mathematica or whatever, or work it out by hand if you really want. But if you play about with it, it should simplify down to something like h bar g dot sine of 2 theta divided by 2 square root delta squared plus g squared. So you get this term on the outside, and whenever you plug everything in, and you take into account what sigma z does to the outer product of the excited states with each other, and you take the sums, this thing simplifies to a sigma y. And if you work out what sine of 2 theta is, so we have all the ingredients we need. You take your normalized eigenstates, just plug it all in, and just let Mathematica do its thing. What will drop out? Minus h bar delta g dot divided by 2 delta squared plus g squared sigma y. This guy is exactly my HCD. So what this is telling us for the case of the single spin is actually very, very elegant. I have a sigma x term which sets the minimum energy gap. So you could imagine that being a field applied in some direction to my system that induces a minimum energy splitting. Then I have a sigma z term, which is like an applied field, and that's the guy I'm ramping. That tells me where I'm sort of sitting along my eigenstates, whereabouts where I'm driving. The control here, if I'm ramping that system and I do nothing else, I just linearly ramp or do whatever ramp I want to the GFT, I'll get excitations. If I started in the ground state, the finiteness of the ramp, adiabatic theorem tells me I'll get some excitations. The counter-diabatic term is telling me that in order to perfectly suppress those, to get rid of any non-adiabatic transitions, I simply have to apply another field in the y direction. So it's somehow the geometry of this very simple system, it sort of drops out and it seems very nice. So you didn't really, somehow it's kind of obvious because we didn't really have an awful lot of flexibility here, did we? We had one field applied in the x direction, you can imagine, to set the minimum gap. One field that we're varying. We don't have an awful lot of freedom on where we're going to apply the control to, so it sort of made somehow, at least intuitively to me, makes sense that it goes in the one other perpendicular direction we have to play with. So this is what the control term drops out to be. Equivalently, you can work it out using this expression. So again, I'm not going to go through that because it's a little bit more involved, but if you take this term, and again, we've got what our eigenstates are here, we know what the theta term is and everything, just plug it in, and if you work out this expression, if you work out that guy, you'll get exactly the same thing as we just saw. So you'll again have something which is given by a bit of a mess of things in terms of how the field is being ramped, the functional form of that g term, but ultimately it's all just proportional to this sigma y. You end up getting exactly the same thing dropping out. Now, I want to have a quick look at why this works. Okay? I think intuitively, like what I was saying before, by construction, this counter-diabatic term kind of, whatever excitations my system wants to get, this just sort of slaps them back down. My system wants to get sort of jump energy levels. I have selected a term to add to my Hamiltonian that perfectly suppresses them. Any excitations get flattened back down. While that's sort of intuitive, it's not really, somehow, it's obviously not what the system is doing. It's not that, there's actually some, little guy there slapping excitations back down into the ground state. That's not what's going on. So there must be something a little bit more meaningful happening at the level of it can only really be at the level of the spectrum. So, but again, I don't remember anyone really digging into this or having a look at it in any kind of critical way until a couple of years ago, whenever a few of us sort of sat down and had a little bit more critically about it. And you can sort of see then it drops. I think it's again, quite elegant, I think quite nice. So why does it work? For any ramp, GFT, the system undergoes perfect adiabatic dynamics if evolved according to this H tilde, which is the H plus HCD, which for our Landau-Zener model is my delta sigma x plus GFT sigma z plus, and then here, this, whatever that mess of things are, let's just call this is just some time-dependent function. It depends on what the ramp is. It depends what functional form I've put in for g. If I'm doing a linear ramp, a sinusoidal ramp, whatever. You can throw any functional form for the ramp at it, and this counter-diabatic term will work. It'll give you perfect adiabatic dynamics. So, but it's just some function times sigma y. And then if we look at the spectrum, we can see why this works. So if I look at the energy between, as I ramp the field, okay, and I rescale it according to what this delta is, then I have two energy eigenstates, okay? So let's me just look at what the energy spectrum is. I have an excited state, I have a ground state, okay? So this is characteristic. If you ever look at the Landau-Zener model and you plot what the two energy eigenstates are, and you plot the energy eigenvalues, this is what you see. You get a gap here, which is delta, and this is what we call the avoided crossing. And this is where it's why the system needs control. I mean, where the energy gap gets small, we know, if you look at what the adiabatic theorem was telling us, if I'm ramping the system, in order for me to have, for that non-adiabatic term to be negligible, either the numerator had to be very small or the denominator had to be massive. One thing that I know is happening here is that the energy gap, there is a minimum. There's an avoided crossing here as I'm ramping through. So if the ramp I'm doing starts somewhere over here and is ramping to somewhere over here, if I do that in a finite time, when I hit this avoided crossing, the gap is too small. If I'm doing the ramp too fast, I will get excitations. Okay? So that's essentially why. So this is what's going to happen if I just arbitrarily ramp the system. But while this is normally the picture we have when we're thinking about the system, I'm saying I'm controlling the Landau-Zener model, that isn't the Hamiltonian that's actually evolving, right? I'm not evolving according to just H, I'm evolving according to H plus HCD. So the question is, what's the energy spectrum that I'm actually evolving according to? So if I look at that guy, so this H tilde, and if I plot what these energy eigenvalues are doing, I get something that looks like this. So, okay, aside from my horrendous sketching, but the essence is you should be able to still see here. In the bare Hamiltonian, so the original guy that we're evolving, the guy that we would need control in, there's an avoided crossing. As I'm ramping through, if I start on some value negative of the field and I want to ramp through to the positive side, I have to go through that avoided crossing. Adiabatic theorem says that energy gap gets small. I'm doing it in a finite time. I'm going to get excitations. By doing counter-diabatic control, that Hamiltonian, that HCD term that I add, modifies the spectrum. It modifies the spectrum in a very precise way. It modifies it such that instead of having an avoided crossing, it pushes the energy levels apart. So it creates large spectral gaps where there had been small spectral gaps, which then means that it's very easy for the system to continue to evolve adiabatically because the energy gaps are massive. So you remember, we had those two competing effects. On the numerator, if we evolve sufficiently slowly, it doesn't matter what we're doing, we will have adiabatic dynamics because H dot vanishes. If I go slowly, like infinitesimally slowly, then the time derivative of the Hamiltonian vanishes, then I get no non-adiabatic transitions. Counter-diabatic driving allows you to do any dynamics you want. You can go arbitrarily fast. How can I go arbitrarily fast? The only way for that term to still be negligible is then if I have large energy gaps. So I have to be messing about with the denominator. That's what the counter-diabatic driving actually does. It says, well, fine, if I want to go at some rate, the faster I want to go, the bigger this gap becomes. In fact, that's something which essentially we thought about a couple of years ago, me and Defner over in the US. Whenever we started collaborating, this is the first problem we started playing about with. So it's, all right, I want to wrap up now in the next sort of 10 or so minutes so we have a bit of time to sort of relax and before the next session. So I will switch to a couple of slides just to tell you about a couple of projects that and you'll see that I have been building a career messing about with two-level systems, and it's been very, very productive. So it's quite nice. Any questions on this at this point before I switch over to the slides? No? Yeah. Why along Y? I think here it's just because there's not really that much more freedom for us to well, actually, yeah, no, you do. So there is a modification of this, because one of the things is that applying that Y field may not be the easiest experimental thing to do, because there's actually a complex number that's sort of swept under the carpet in here. So how do you physically realize that? People realize, well, actually, you could get the same effect by doing a transformation and put it in what they call a local counterdiabatic form, where instead of having a sigma y term, you express everything in terms of the sigma x and sigma z only. And then you can have time dependence on both of them, and so you'll modify the gap, you'll vary delta, and you'll vary the field in a very particular way, and you'll get exactly adiabatic dynamics again. It's a little more subtle again, so I think you're right. It doesn't necessarily have to be sigma y. In fact, this is not a unique way of achieving the control. It's just what drops out whenever you do the counter-diabatic driving this way. So, yeah. Okay. Now I've been sitting for ages, and I may fall asleep if I sit for any longer. So I will stand up and mention just a couple of things that we did on this. You'll see pretty much what I've been doing the last couple of years. So what can we do with the quantum control? With this question, what we've been looking at and what we've sort of understood, you can write down and derive a control term that follows just directly from the adiabatic theorem. So you derive adiabatic theorem, it tells you precisely how the system reacts to a finite time drive. You use that information to exactly counteract those effects. What we were interested in then is, I mean, there's some interesting questions then. Well, once you know how to control a system, you can start asking, like, well, what sort of resources are you investing into it, or what sort of other interesting physics can we learn from it? So some of the things I've been messing about with would be, I've done stuff on we'll talk a little bit now about the speed limits in these instances, and a little bit on this Kibble-Zurek. I probably won't get into any of the other ones. But something which is quite nice and some, is thinking about the theme of the conference here, the school, is the thermodynamics of control. One of the nice intuitions, one of the nice things I see from the counter-diabatic driving in this kind of very clean way is there's a nice intuitive way to think about the resource intensiveness of control. So what are we doing? We have a Hamiltonian, we have some system we want to control, and then how do we achieve control? Well, we have to slap on an additional Hamiltonian term. That's just an energy. So what the counter-diabatic term also gives us, not only does it give us a way to control, it also gives us at least an ad hoc notion of how energetically costly is it to control the system. The more intense that term is, the more energy we have to invest in order to control the system. And again, you can kind of intuitively see where that comes from when you look at what the counter-diabatic term did to the Landau-Zener model. What it did is it pushed the energy levels apart. The faster you want to go, what we'll see, I think, next, is the faster you want to go, the more those energy levels get pushed apart. If you want to go really, really fast, you have to push them really, really far apart. Okay, this was just Landau-Zener model that we were talking about. So where I first started playing about with this was exactly, you can go and do these calculations now essentially yourself and have a look at how the speed of the dynamics enters into the speed of the control dynamics tells us something interesting. So if I want to achieve control, I have my two-level system. I want to start somewhere here in, let's say, some ground state, and I want to ramp it through to this guy. I know exactly how I can do it. Okay, the notation has changed a little bit. I have my bare Hamiltonian, that's my H, that's my counter-diabatic term. If I evolve according to this total guy, I know that no matter what ramp I do, I will always stay in this ground state. And I know that will happen because that additional term pushes the energy levels apart in just the precise sort of way where the system will always stay in its ground state. What we did, what we were interested in saying then is, well, how does, like, what happens, like, can we understand something at the level of the speed of the dynamics? So we used some tools from quantum speed limits. Don't need to know anything about those. It's suffice to say that all we actually did was look at how fast the system was evolving. So it's maybe a little hard to see here, but we defined an overlap, and then the speed was just the rate of change of that overlap. That's really all we were doing here, okay? There's a whole machinery of quantum speed limits that we were employing, but at the end of the day, all we were calculating was the rate of change of a fidelity. That's basically it. If you calculate this guy in this context, we found something where we saw something very, very elegant, I think, which was far away from the avoided crossing, regardless of how violent the ramp was, the speed that was coming out from this quantum speed limit calculation, so just the rate of change of this guy, all of them collapsed on top of each other. So you see here, we have we're doing a linear ramp, and we're saying, imagine I fixed the energy gap to be something, it doesn't really matter too much, and I'm saying I'm taking a total duration of 10 to the 3, so really, really long. That is so long that the time derivative of the Hamiltonian is basically 0. That's essentially adiabatic. And then I'm taking a faster ramp, and then I'm taking a really fast ramp. So where, like, I'm really kicking the system, I'm almost instantaneously jumping from one value of the Hamiltonian, ramping it right through to the other. What we found, or what you'll see if you calculate these things, like the rate of change of this overlap, is that in certain regions, all of these speeds all collapse on top of each other. But once you get close to the avoided crossing, this is where you start seeing differences in the rate at which this fidelity is changing. So the controlled evolution ends up giving rise to these kind of curious peaks appearing. Now, we can understand the origin of them when you think about what happens with those energy levels getting pushed apart. The size in which the amount of energy you have to invest in order to create those big energy gaps, you can find is proportional to just how big the magnitude of that control term is, and that's what gives rise to these peaks. What was sort of curious from here is that this was very reminiscent of this Kibble-Zurek mechanism that I mentioned at the start. Now, the adiabatic theorem, tells us how we need to manipulate a system in order for it to, stay, for the dynamics to be perfectly adiabatic. I said that the Kibble-Zurek mechanism is essentially a sort of more careful reformulation of that into thinking about, well, how does a system react if I do a non-adiabatic transition? Like, can I say something a little bit more precise than just what the adiabatic theorem was saying? And what Kibble-Zurek says is that the response of a system can be split up into essentially two dynamical regimes. One is what we call adiabatic, and that is where the energy gaps, the intuition here is when the energy gaps are sufficiently big that when I'm ramping the system, it doesn't get excited. And so you can sort of see the essence of the adiabatic theorem is there. If the energy gap of my system is really large and I'm ramping the system, but I'm ramping it slowly in comparison to the energy gap, to the inverse of the energy gap, I won't get excitations because of the adiabatic theorem. But if my spectrum is doing something interesting, like in the Landau-Zener model, where it starts large, and if I was ramping the system, let's say I was doing that linear ramp, exactly what we've been talking about all afternoon, if I was ramping from here to there, I have to go through this avoided crossing, so the energy gap isn't always large. There's a point where it gets small. The Kibble-Zurek mechanism basically says that there is a point in this dynamics where the gap gets just small enough that that mn dot term that was at the essence of so much of our discussions today starts to play a significant role. That's where the transitions, the non-adiabatic transitions start to kick in. That's what Zurek described as the impulse regime. Adiabatic regime, energy gap's very big. Everything I do, essentially, the system doesn't get any excitations. But at some point, the energy gap gets small enough compared to how fast I'm ramping the system, I'll start getting excitations. And how he derived it, sort of a little bit heuristically, a little bit hand-wavily, saying that, you know, there's a point where the rate at which I'm changing the ramp, everything they did mostly was for linear ramps, the rate at which the ramp is changing is going to be equal to the inverse of the energy gap. At that point, signals the transition between adiabatic dynamics and this impulse regime. And there's a whole framework that goes into this that we're not going to be too worried about. But this is what the Kibble-Zurek mechanism was telling us. You see, it comes essentially from the adiabatic theorem. What we saw in our control dynamics, whenever we were messing about with it 4 or 5 years ago now, was something that felt very reminiscent of the Kibble-Zurek picture. There is a regime in here where the speed of the control dynamics was all universal, essentially. There was no difference between how fast I was ramping the system. I could see no differences at all here. While whenever I needed control, whenever the system, the magnitude of that control term became non-negligible, then I started to see some differences in the behavior of this speed. You know? And this felt very sort of Kibble-Zurek-y, really. That's sort of where we left it for a couple of years. But it was always sort of lingering that somehow there was something in there that we could understand what the response of this is, or could we understand something about the non-equilibrium dynamics captured by the Kibble-Zurek mechanism by looking at the controlled dynamics. And that's, I guess, punchline is that yes, we could. So, okay, that's maybe not so relevant to show you. I'll just stick on this. We'll go back a slide. I think it wasn't so, maybe it's not so surprising that was going to happen, because remember, the controlled Hamiltonian, the counter-diabatic term is proportional, inversely proportional to the energy gap, okay, to the difference between, there was an EM minus EN in the denominator. The Kibble-Zurek mechanism, what it predicts essentially is how many excitations you get. The dynamical response is dictated by the underlying equilibrium properties of the system. So if I have a many-body system, I have critical exponents, all these different interesting things. They are all fundamentally related to how energy levels are changing, like how energy gaps are closing. The fact that the counter-diabatic term, so the control dynamics, is built on, it explicitly involves things to do with how energy gaps are changing, it maybe wasn't so surprising that if we thought about what the control dynamics was telling us, that we would recover some Kibble-Zurek-like behavior. But it was nice that we finally went through it and we, you see it explicitly. So what I had in this other slide was essentially where we did it for the Ising model, but in fact, like you see the plot here, this was the Ising model. It looks very, very similar to what we had for the Landau-Zener. And in fact, we did it for the Landau-Zener, where you can do certain sort of Kibble-Zurek-like arguments in there as well. But really, the takeaway message here was just that you can take your control dynamics and you can study non-equilibrium phenomena by looking at the behavior of the control. And I think this is a nice insight. I think this is the kind of, I think I'll wrap up now in a second. This is the kind of main takeaway, I think, that there's control. You can achieve control in a number of ways. We talk about the counter-diabatic driving as a kind of zeroth order, just the simplest way to achieve it. You go to the adiabatic theorem and you just get it for free, essentially. But whenever you start studying the dynamics of that guy, if you can control a system, you somehow implicitly know what would happen in the absence of that control. And what is that? Well, that's non-equilibrium dynamics. And we're very interested in non-equilibrium dynamics. There's a lot of interesting stuff to do there. So what this, at least, what I thought about when we were working on this work was a kind of first proof of principle. There's a well-established non-equilibrium phenomena, this Kibble-Zurek mechanism. Can we extract something to do with that from the control dynamics? And what we found was, with the right combination of this speed limits stuff that we didn't talk so much about and the control dynamics, you can recover exactly Kibble-Zurek-like scaling in the controlled evolution. So I thought this was quite nice. The last thing just to mention is, well, I only focused on this counter-diabatic driving There are a host of other ways that you can achieve control. So like Francesco was asking, like why was it the sigma y? And I was saying like there are ways in which you can achieve the same dynamics without having to add on this additional Hamiltonian term by doing something else. So I think very, very crassly putting it, or very roughly, there are kind of two major camps to achieving control. I talked only about one type, one subset, one particular technique that falls within the realm of these shortcuts to adiabaticity. So there's this review paper from 2019 where they went through the whole suite of different things. So I mentioned a little bit this inverse engineering. The approach to inverse engineering we went through there was, again, kind of like the very simplistic version of it. There are much more refined ways of achieving, of inverse engineering the dynamics. But that's also not the end of the story. There's all these newer techniques like variational control, and there's something called like adiabatic gauge potentials, which are really cool. These are very new things from Anatoly Polkovnikov and his collaborators, where there's a direct connection back to the counter-diabatic term. And in fact, a lot of these control terms in these shortcuts to adiabaticity, there's a kind of thread that runs right back to the counter-diabatic term we derived. So if you understand that, it's kind of a good starting point to start exploring all of these different analytic techniques that can drop out. But that's just one camp. There's another huge established area, which is what sort of, again, very broadly called is optimal control. Again, that's a kind of very broad catch-all term. On one hand, like it captures all of the numerical approaches, so a little bit more brute force things where you say, well, I know what dynamics I want to achieve. So again, I want to ramp a system, or I want to do a state preparation. So I fix what my target is, and then I set some constraints, and I numerically optimize. It's in that instance, it's maybe a little bit more rough and ready. It's kind of like a very practical toolbox. You give it to your constraints, and off you go. It benefits in that respect over the counter-diabatic driving that we were doing, because you're guaranteed for it to be more physically implementable. So like I said, something that we didn't really touch on was that these counter-diabatic terms are very often horrible. Like they're not experimentally implementable at all beyond the like single spin or maybe a couple of spins. Optimal control approaches, you can basically bake in whatever constraints you want. But it would be wrong to suggest that optimal control is a purely numerical approach. There's actually there's a whole framework of analytic approaches as well in optimal control. So this review came out, I think, just a couple of months ago, and it really is pretty much the state of the art in optimal control. So if you look at these two things, you'll find common themes across them all, but there's still a huge amount of directions to go, I think. So I think with that, we're coming on to 3:45. I rambled on for a good bit, so I think maybe we'll take 10 or 15 minutes before the next lecture. But if I'm here all week I'm here until Friday morning anyway, so happy to chat, or if you have any questions right now. But yeah, otherwise, all good.
Please, here. Here, take the box.
Hey Steve. Could you do this in, say, real time? So say, for example, you had an unwanted source in your Hamiltonian, like a noise source, and it was like causing unwanted transitions that you wanted to kind of suppress. Is there a way that you could actually implement this in real time by using, say, some sort of measurement scheme where you...
There are some, so I think in both of those reviews, there'll be some sections where they discuss feedback control. So where you have something and you look at the system evolving, and then you like do a measurement, or you learn something about it, you infer something, and then you allow it to kind of cycle through. Not a huge amount done in that direction, I mean, but there's a little bit. On the flip side, like the point about noise, like one of the things that I'm very interested in now is, well, what happens if you have some random fluctuations? Like there's been a lot of stuff done in these control terms, especially the shortcuts, like these analytic techniques. We are always, I think most people in this room, I have a funny feeling, are theorists. Any experimentalists? None? Oh, Jake. Oh, okay. But yeah, so we were sort of implicitly assuming that we can implement these control terms perfectly. And so one of the important things to look at is, well, what happens if you have some perturbations, or what if you don't perfectly implement the control pulse? Like how detrimental is it? In general, a lot of these control techniques are still reasonably robust. You can have a bit of fluctuations or a bit of error in the pulse, and you'll still get pretty high fidelities. But what hasn't been done, and what we're digging into now, is, well, what happens if there's like intrinsic disorder? So if I have like a system, now it gets particularly important if you go to like a many-body system. If I have an exchange, or like just standard like spin chain, and I have some disorder on each of the different sites, I get localization. If I want to do transport or do something there, how do I overcome that type of noise? That's much trickier, because these techniques are basically useless in that instance. So we're working on sort of hybrid approaches. In fact, that's one of the most exciting things I think that comes from these two reviews that people are starting to do now, is they're starting to realize there's a lot of there's no point in restricting to just one particular type. If you can cherry pick a few different sort of combining aspects of these analytic techniques, from shortcuts with the numerical approaches from some optimal control. Obviously, it's in vogue, so people are just throwing machine learning at everything and going like, "Hey, Nature papers." So you can, but you can pull all of these different things together, and what we're finding is that it's giving us some routes into controlling more complicated systems. But I think there's huge, one of the things I'm very interested in is really at the fundamental level, just the controllability of systems as well. So I think what we see is that there's nothing inherently stopping us from controlling systems. But adiabatic theorem, again, shows us that the microscopic description of it is kind of fundamental in terms of how it's going to respond to any time-dependent changes in it. So there's something very interesting in just the fundamental controllability of the system by looking at, well, what are the spectral features, how does that impact how controllable it is? I definitely went way off on a tangent there from your question, but...
Cheers.
So, if there are no more questions, we can thank our
I think it's needed.
speaker again.
Okay, so we'll have a 5-minute break, as Jake was saying, use the microphone and everything, so apologies. And then Professor Bob